All right, so welcome back to OneClass. Again, my name is Joey. I'm going to be your, this is SCH for you, so Chemistry 12 for the Ontario curriculum. Again, my name is Joey. I'm currently an intermediate senior division secondary school teacher, a teacher candidate more specifically. I'm hoping to get my OCT certification very shortly from now on. And again, my main subjects of teaching are specifically chemistry and in science, and as well as in music as well. I'm also planning to get my math teachable further down the road. So here at OneClass, if you're tuning in for the first time, thank you so much for joining us. What we're doing here at OneClass is we are delivering free online lessons, particularly in secondary school, in the secondary school subjects in mathematics and chemistry at the secondary school level, as well as in the university and college level. So if you're tuning in for the first time, thank you for watching and thank you for tuning in. And I hope that you find these lessons very educational. What we're doing is we're trying to combat the COVID-19 closures of schools. So we here at OneClass, what we're doing is providing online and free resources for you students at home. Or if you're a parent or guardian watching, please, what you can do is you can just send this link to your kids at home, and maybe they can tune in as well, and learn with me as I journey along in this in these couple of courses in chemistry and as well as in math. So without further ado, let's get started and let's pick up where we left off last week. So what we're doing today is we're exploring this topic of organic chemistry. So we've been in this unit now for quite a bit, and what we talked about before, last week, we talked about naming organic compounds, specifically alkenes, alkenes, and alkynes. So recall that alkanes have a single bond, alkenes have a double bond, and alkynes have a triple bond. So that's what we've been talking about for the past bit. And we talked about branched alkyl groups also, so like methyl, ethyl, propyl, butyl, etc. as well. We talked about those things as well, and we talked about naming these organic compounds. So we named already. We did a bit of naming last week, and if you missed that, maybe go back to my last week video if it's posted on OneClass, and you can talk about. Can we watch my thought process as to how to name these organic compounds? What we're going to do today is we're going to do the opposite. So we're going to take the name and then we're going to draw the organic compound. So we're going to do a couple of that first, and then we're going to jump into a new concept about aromatic compounds, and we'll talk about those compounds more in detail as we get there. So let's do the opposite of naming, but let's draw these chemical compounds. So what we've been doing before, we've given the diagram, the line diagram, or the structural diagram, or the condensed structural diagram to be more specific. And what we did was we wrote down the IUPAC name, or we wrote down when we named these organic compounds. So what we're doing is we're going to do the opposite now. We're given the IUPAC name, we're given the name of the organic compound, can we draw it? So let's do the first one. The first one's pretty easy. The first one here is pentyne, right? So let's go. So if I have here, this is pentyne. So when I look at the name, I'm looking at two specific things in this case. For example, this is my first example. I'm looking at the ending first. The ending tells us what kind of functional group or what kind of organic compound we have. So this ending is YNE, and as you might recall from previous videos, INE or YNE means there's a triple bond in my organic compound. Remember alkynes at YNE, the ending YNE means that there is a triple bond in this case. There's no number here, so which means I can infer that my location of my triple bond, so location of triple bond is on carbon 1. So I'll say at C1, at carbon 1. And then, so that's my first two pieces of information that I know. Because if it's not on carbon 1, I would have some type of number in this slot here. I'm going to do this in red. There should be a number in this slot, right? It's pent1-ine. We can infer this is at carbon 1. There should have been a number here where it drew in red. And then lastly, I'm dissecting this name. This here is pent, right? And the pent here refers to the longest chain of carbons, right? So the longest chain of carbons. And pent here, as we talked about previously, our prefix is pent. A good way to memorize this pent is pentagon, which means a pentagon has 5 sides, right? So it means I have 5 carbons, 5 C's. So knowing these three informations, we can actually draw our organic compound, right? I would have to draw simply a 5-chain carbon. So let me do a condensed structural diagram for you folks here. So this would be a C, 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 bond C, bond C. So this is a 5-chain carbon. On carbon 1, it's the location of the triple bond, right? So I would have to do a triple bond here, which means actually affects my geometry here. So I'm going to have to do, so it's C, triple bond C, and then it would be a linear, so bond C, and then it could go down like so. So that's going to be my condensed structural diagram, and I'm going to have to fill in the hydrogens, right? So for example, this one has 1 H here. The second carbon here has no H's because it has already creating 4 bonds. The third carbon here has 2 hydrogens to saturate it. This one also has 2, and this one has 3, right? So because again, carbon's making 4 bonds, and this here is pentyne, or if you want to be more specific, it's pent-1-ine, to locate that the carbon is on the location of the triple bond is on carbon 1. So we can check our answer, right? And how we do that is that we'll just name this. We just go backwards, right? Our longest chain here is 1, 2, 3, 4, and 5. Our triple bond is located on carbon 1. So this here is our triple bond. So that's good. We have 5 carbons, which is pent. 1 is our location of our triple bond, and YNE is our ending for a triple bond. So this here is correct here. So we got that correct, which is awesome. So, sorry. Now what we're going to do is so pentyne, we're going to move on to alkyl groups, and these are the branched alkyl groups. So let's look at that for a second here. Let's do that. So this is number 6. So let's draw number 6. And I'm going to start doing some structural diagrams, or sorry, some line diagrams for you so we are more familiar with that. This is 278 trimethyl decane, right? So this is our name here, 278 trimethyl decane. So again, let's break this down. I'm actually, if you're in the chat here, maybe wave hi or something like that, and let's talk about how would we approach naming or drawing this chemical compound. What are the things we're looking for when we're dissecting this name here? What are we doing here? So maybe take a minute to look over that on your own, and we're going to talk about, we'll take this up and I'll walk you through the thought process as we're drawing this chemical compound. If you're in the chat, maybe wave hi and talk about how would you approach this problem here. 278 trimethyl decane. So again, the first thing I would look at is I would actually look right to left, and because the ending of the organic compound, or the naming, the end of the chemical name means a lot, because it means that it's going to be the type of what kind of functional group I have. Do I have a single bond, triple bond, or single bond, double bond, or triple bond, right? So these are all good things to note. So let me do this in blue. So I'm working from right to left. So I'm doing ANE first. So what does ANE mean? ANE means that I have all single bonds in my diagram here. So I have single bonds. I don't have a double or triple bond. So it's all carbon, single bond carbon. This dec here means that a decagon, how many sides does a decagon have? It has 10 sides, which means a carbon chain here is 10, right? 10 carbon chain. That's going to be my longest chain. I have methyl groups here, right? A methyl group means that I have a branched alkyl group, and it means that I have besides my longest chain of 10 carbons, I also have these kind of methyl groups. So I have a CH4, which is a methane, but it's going to be stuck to specific things. To these specific carbons, and I'll do this in red. Actually, I'll do the branched stuff in red, so make it easier for you to see. So methyl groups means I have a I have a one carbon side group, so one carbon side chain. And then this tri means I have 3 of these, right? I have three 1 carbon side chains, and this is the location of side chains. So 278 is the location of 1 carbon side chain. So with these 5 types of 1, 2, 3, 4, 5, with 5 types of information here, I can actually draw my my organic compound. I'm going to work from right to left. Sorry, right to left. Yes, right to left, right? So again, single bonds here. I have a straight carbon chain. So again, it's all single bonds, right? So I can write. I'm going to do a line diagram here. So I have a 10 carbon chain. So I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And let me count that really quickly in blue. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's good. And then I'm going to do this in red. And again, I have methyl groups, which means I have 1 carbon side chains. I have 3 of them, and the location is at 2, 7, and 8. So at 2, 7, and 8, I'm going to put a 1 carbon chain. So at 2, I'm going to put a 1 carbon chain here, because this here is a carbon here. This little point here is 1 carbon. At 7, I will have another one, so I'm going to stick another one here, and at 8, I will have another one, like so. And this here is 278 trimethyl decane. So this here is my longest chain. I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't count another way. If I count it from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it gives me the exact same numbering. So it doesn't matter if I started from here or here. So this here is my correct answer. This is 278 trimethyl decane. And again, I can check my answer by naming this compound, right? And I can go backwards, and I'm going to get 278 trimethyl decane. So that's this compound here. So let me work on number 7 for you. Number 7 here is 5-ethyl. Let's see, 5-ethyl, 2,4-dimethyl octane. So again, take a few minutes, dissect this name. What information is it telling us? And then we're going to draw the compound here. So again, take a couple minutes to do that it's just take a couple minutes to do that. Nobody's in the chat yet. I'm actually very surprised. So again, I'm working from right to left, right? Because I want to know the stuff on the right-hand side, or sorry, this is your right-hand side. On the right-hand side matters much more in terms of what it tells us about the entire main chain. So we have an A and E here. Again, we know it's a single bond, single bond to carbon. So carbon, I'm going to say just C, single bond C, C bond C, so single bond carbons. This oct here means there's 8 carbon chain, right? So I have a 8 carbon chain, 8C chain, and then I'm going to do all this stuff here is in our side chains, right? Our side things here. So I'm the methyl group. Again, I have a 1C side chain is methyl. I have 2 dimethyl means I have 2 of these one carbon side chains, and the location, this is the location of the 1 carbon side chains, right? So it's kind of what we did in our previous example. However, we actually threw another side chain for you. This ethyl here is another side chain. This here is a 2 carbon side chain. Because remember, F here means 2, and the location of that is at 5, right? So this is the location of this is the 2 carbon side chain. So this 5 here refers to this location of the ethyl. The 2, 4 refers to the methyl, or the 2 methyl groups that are in the side chain. So given all this information, we can draw it. So let's draw from right to left. Again, I'm starting with my blue. I'll write it in black. So again, I have an octane, right? I have my 8 carbon side chain is going to be the base or the foundation of my compound. So I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 carbons first. So I'm good with that, and they're all single bonded together. That's awesome. I'm done with the blue, and then I'm going to shift to red here. Actually, let me label the carbons for you. This here is 1, 2, 3, 4, 5, 6, 7, and 8. And then what I'm going to do is I'm going to now deal with, I'm going to work from right to left, right? So I'm dealing with this 2,4 methyl, right? So at carbon 2, I'm going to have a methyl group. So I'm going to draw a methyl group like this. And then at 4, I also have a methyl group, right? So at 4, at carbon, this here is carbon 2. And this here is carbon 4. At carbon 4, I have another methyl. So again, it's just a 1 carbon side chain, right? So I have those two things. And then I'm going to deal with my ethyl, right? So these 3 things are dealt with. And then I have my ethyl. And the location of the 2 carbon side chain is at carbon 5, right? So this carbon 5 here is going to go 1. Oh, sorry. It's going to go 1 and then also 2. So it's a 2 carbon side chain in this case. And now this is my correct answer for this question here. I have 1, 2, 3, 4, 5, 6, 7, 8 will be my octane here. At carbon 2 and 4 are in both my methyl groups, and then at carbon 5, I have my ethyl group. So this here is my correct answer for number 7. So I'm going to leave that up here, the answer for you up here, while I write down number 8. And then I'm going to also do question 9 here, because again, this is very, very, very important. These things are very important. As we build our foundation of organic chemistry, we're going to need these rules consistently over and over again. So this is very, very important. So this here is number 8, and then I'll do number 9 with the cyclic hydrocarbon. So it's something we learned about last week, and I'll bring that back as well. This is 5,5. This is dimethyl, and then this is 3-heptene. So this is the old IUPAC name. Sometimes I can rewrite this. I can also rewrite this as 5,5-dimethyl. And it would be hept-3-ene. So again, these two are the same chemical compounds. The only difference here is in the IUPAC name. 3-heptene here, or hep-3-ene. This 3 here just means the location of the double bond here. I personally like putting 3 right beside, in between hept and ene. So it's very, very specific as to, the ene, or the double bond in this case, refers into it's the 3rd carbon that's being double bonded. So I like the second one. I like the second option here when I'm naming it. And I think the second one is the newer IUPAC name as well. This, again, this worksheet was made a bit older, so we follow, this is the older IUPAC name here. But this here, I'm gonna introduce you to the newer IUPAC name. So again, take a couple of moments to figure this out, and we're going to break it down it's the exact same way as we've been breaking it down before. So again, I'm going to do my blue in my parent chain and then my red in my side chains. So how would I do this problem? How would I approach this problem? So I have 5,5-dimethyl hept-3-ene. So 5,5-dimethyl hept-3-ene. So I'm going to start with I'm starting with hept-3-ene as my first thing to do. So again, I'm going to do it in blue, and let me just take this up with you. The first thing we're going to do is right to left, right? So we're working from right to left. So again, we have here this ene refers to a carbon double bonded a carbon, right? It's an alkene, so it's a double bonded carbon. This 3 refers to the location of my double bond, so location of C bond C. And this hept here refers to my main chain. How many carbons are in my main chain? Hept, a heptagon contains 7 sides. So it's a 7 carbon chain here. 7 carbon chain. And then in red, I'm going to do my side stuff, right? This here, this 5,5-dimethyl business is my side chain, right? 5,5-dimethyl, what does that mean? We actually looked at a dimethyl example already. Again, methyl here is my 1 carbon side chain. The di refers to, I have 2 of these things. I have 2 1 carbon side chains. And the 5,5 refers to the location, right? Location of 1 carbon side chain. So how would I do this problem? Let me draw this out. So let me draw out the blue the blue things first, the main stuff. So again, I have a hept 3-ene. So my main chain is going to be contained of a seven carbon chain, right? So I have 1, 2, 3, 4, 5, 6, 7. So let me do this in blue. I have 1, 2, 3, 4. Sorry, that's a 9. 4, 5, 6, 7. And then what I'm going to do is my location, I have a double bond at carbon 3, right? So I'm going to switch this, and I have a double bond at carbon 3. So I'm going to draw a double bond at carbon 3, which is awesome. It's going from 3 to 4, right? So it starts at 3, right? The location of my double bond, it starts at 3, and then it goes to 4. So hep3-ene is taken care of. That's great. And then now I'm doing my side chain stuff. I have 5,5-dimethyl. So the location of my 1 carbon side chain, both of them are located on carbon 5, right? So this is carbon 5 over here. I'm going to do 1 methyl group like this and 1 methyl group like that. So that's going to be 5,5-dimethyl on carbon 5. So a lot of students, when they see 5,5-dimethyl, they just write an ethyl group like this. This here is an ethyl group. It is not a dimethyl group. So you have to make sure that the methyl group is both of them are connected to carbon 5, just like this. This here is 5,5-dimethyl. I have 2 methyl groups. Again, this here is my first methyl group here, and my second methyl group like so. So again, this here is 2,5,5. This entire structure is 5,5-dimethyl hept3-ene, and that's gonna be my answer for number 8. All right, let me do an example with a cyclic hydrocarbon. So this is number 9. It's not on this sheet. I'm just gonna draw it out. I'm just thinking in my head. I'm creating the problem in my head. Let's give you this problem here. This would be let me try to think. Let me give you 3,3-dimethyl, and this would be a cyclohexene or cyclohexene in this case. I could have rewrote this as just cyclohexene, and the 1 is implied. That the double bond here is implied. It's on carbon 1, but maybe I'll write hex 1-ene for you, so it makes it a little bit more clear. So again, how would we draw this organic compound? So again, take a minute to think about this problem here. How would we draw this organic compound? And again, we have a cyclo group now, so it's different. All right, so let's work this problem out. So we have a ene here. I'm going to work from right to left. We have an ene here, which means I have a double bond, right? I have a alkene, which means it is a carbon double bond to carbon. Its location is it's implied it's located on carbon 1, so CWB on carbon 1. And then I have a hex here. Hexagon has 6 sides, so it's a 6 carbon chain. And the cyclo here means that it's in a cyclic form. So this is actually a hexagon. So this here, because it's 6 sides, it will actually be a hexagon. So I'm going to make a hexagon with my cyclo group. So it's going to all be connected to one another. It's cyclic, or it's circular. Not really a circle, but you get what I mean. And then 3,3-dimethyl just means the side chain stuff, right? So again, I have methyl group is a 1 carbon side chain. I hope you're familiar with methyl groups. We've done so many methyls now at this point. Side chain. The di refers to, I have 2 1 carbon side chains, and 3 just means the location, right? The location of 1 carbon side chain. So let's draw this out. I'm going to do black now. I'm switching gears. So again, I have cyclohexene. The stuff in blue is cyclohexene. So again, I have a 6 carbon chain, and it's a hexagon. So let me draw the hexagon, because it's a hexagon, right? So let me draw a hexagon here, and then I'm going to label. I have a double bond on carbon 1. So let me make the top part carbon 1. This is 1, 2, 3, 4, 5. Oh, sorry. uh, 5 and 6. So on carbon 1, I have a double bond, right? So it's going to double bond from carbon 1 to 2. So I'm going to draw a double bond like this, like so. So that's good. And then I have, so all the blue stuff is now finished. So this is cyclo. I have a hexagon here. It's a 6 carbon chain. So 6 carbon cyclic chain in this case. And I have a double bond on carbon 1 here. So that's good. My red here is 3,3-dimethyl. So I have 2 1 carbon side chains, or 2 methyl groups on 3, right? So I repeat 3 and 3 together because I have 2 methyl groups on carbon 3, right? So I have 1 methyl group like this and 1 methyl group like this. So this here is my 3,3-dimethyl cyclohex 1-ene, and that's going to be my solution for this problem here. 1, 2, 3, 4. Yeah, so that's good. Sweet. So that's gonna be my drawing for this one. So I hope you're more familiar with drawing organic compounds, and we're gonna go back and draw and name a lot. And when I say a lot, it's actually a ton of organic compounds. And this is only with alkenes, alkanes, and alkynes, and with cyclic structures. I'm gonna introduce you to the concept of an aromatic compound now, and these also follow other rules as well. So let's look at that. So we stopped here with naming branched alkenes. We're going to move on to this topic of aromatic compounds. So let me describe to you let me define what an aromatic compound, and we're going to do this for the next half an hour of our lesson here. Let's see. Let me just look. Yeah, I'm going to do aromatic compounds, and I'll probably do some reactions of our hydrocarbons, and maybe we'll get to reactions of aromatic compounds. Actually, let me just do reactions first, and then we'll jump into this new topic. So let me do reactions of hydrocarbons first. I just don't like how they reactions. So I'm doing this reaction, and then I'm doing this reaction as well. Yeah. Let me do reactions first, and I'll go back and do aromatics, because reactions are important, and I want to wrap up alkanes, and alkynes before I jump towards the next topic here. So this is reactions of hydrocarbons. So again, when I talk about hydrocarbons, it's specifically alkanes, alkenes, and alkynes. So, okay, so let's do that first. So again, with alkanes and alkynes, I have one general, the general first one here is a combustion reaction, right? So the first reaction I'm going to look at is a combustion reaction. And we're actually very familiar with what a combustion reaction is. You looked at this in grade 10 and in grade 11. So remember, if you remember from grade 10 and grade 11 chemistry, or grade 10 science and grade 11 chemistry, we have something like CH4 plus O2 yields, this is CO2 plus H2O, and I can balance this chemical equation. In this case, it's I have a 2 here, and then I have a 2 here as well. So this is a balanced chemical equation, right? 4 oxygens, 1 carbon. Yeah, for this balanced chemical equation. And we talked about this is a complete combustion reaction, right? So this here, and I'm more focused on the CH4. I defined the CH4. We knew that this was methane. But this here is also a hydrocarbon, right? This is a methane. It's an alkane, right? So this here is a combustion reaction, and we can actually combust alkenes and alkynes as well. And I can show you the structural, and we can always balance these chemical equations. And so a combustion reaction is something we're already familiar with. Combustion reactions, we burn or we oxidize. Or not, we don't oxidize, sorry. We just burn or we add oxygen to a hydrocarbon, and it makes carbon dioxide and water. In an incomplete combustion reaction, if you recall, if I burn a hydrocarbon or a methane or something like that, I'm going to get a carbon dioxide, water, but I also get carbon monoxide. I also get soot as well, which is solid carbon. That's good. That's a combustion reaction. We're already familiar with that. And then there's something called a substitution reaction. So this is something that's new. So this is a substitution reaction. And these are going to be really important. A substitution reaction. Actually, I want to do this I was going to do this in black. Sorry. Let me rewrite that for you. CH4. And this is a gas form. Plus O2. This is 2O2 yields 2. Is it? No, this is just CO2 plus 2H2O, right? Yeah. And this here was our hydrocarbon. or in this case, it's our alkane, right? In this case, because it's methane alkane, right? Sweet. And then what we're going to do is we're going to talk about our substitution reaction. So what's the substitute reaction? In this case, this note here defines it as a hydrogen atom in the alkane is replaced by another atom or group of atoms. So I am substituting something. So in this case, let me draw ethane for you. I'm going to do an example of a substitution reaction here. So let me actually, they use methane, so maybe I'll do methane. So methane, CH4, what it does is if I substitute, I'm going to replace one of these hydrogens. So I'm going to replace one hydrogen here with another atom. So in this case, they did chlorine, so I'm going to do the same thing. I'm going to chlorinate it, or I'm going to substitute it with a chlorine. And it's going to become CH3 and Cl, right? You can see here that I replaced one of these hydrogens with a chlorine, and it actually gives off H2 gas. And I can balance this chemical equation as well. It actually gives off H2 gas. So this chemical reaction would have, this is 5. Let me just balance this. Do I need to balance? Actually, I don't know if it actually gives off H2 gas. It might be maybe just the H plus ion, depending on because this reaction of substitution is actually very, very volatile. This is a radical halogenation, which is actually very, very volatile. So I'm not actually sure what the byproducts are. This could be a H plus, it could be a H2 gas, depending on the reaction itself. It's probably a mixture of both. So I'm not going to balance this actually, because it's actually the mechanism is actually very, very complicated. It's not something you look at until about like first year, second year organic chemistry, when we talk about what's the mechanism behind radical halogenation. So I'm going to leave that for now. I'm just going to put Cl2, and the catalyst in this case is actually UV light. So if you UV light and heat would give you heat is this triangle here. Let me just define this. This is UV light, and this here is heat. So heat and heat. I'm not actually sure what temperature it is, but it's if you add heat and you add UV light, it's going to halogenate or substitute this hydrogen here. It's going to become a Cl as well. And this substitution can go on and on, right? As you can see, I can do another substitution, so another Cl2, and I can actually substitute another hydrogen. So I would get CH2Cl2, right? And as you can see, I replaced one hydrogen with another chlorine, and then I could actually do it again and again and again till carbon, to this here, tetrachloromethane would be a fully substituted carbon, right? I replaced all my hydrogens with chlorine, so it's CCl4, and that this reaction can go on and on as well. So I can actually draw the other steps like they did here as well. Very nice, thank you. Will this be saved for viewing at a later time? It will be. I think OneClass is just a little bit behind because there's such a high volume of videos that we've been uploading, because we upload them every day, right? And it takes a longer time for us to upload some of these videos. But I'm very, very, very certain that a viewing will be the video will be viewed at a later time. I'm just hoping that they kind of catch up, because we have such a high volume of videos coming for you. They have such long videos, like it's an hour long, so it takes a while for them to process these videos and to upload them onto their server. So I'm hoping that these videos will be uploaded shortly for your viewing as well, so you can go back and look at what we did today. So thank you. So thank you for that question. So this is a substitution reaction, and again, this works with chlorine, this works with bromine as well. Honestly, any halogens work, but it's usually just bromine and chlorine that we usually use for substitution. So this is an example of a substitution reaction. Specifically, this is a halogenation. So, or specifically, this is a substitution, and then here, this you can say this is actually you can think of it as just a substitution reaction here. And then I'm going to do an addition reaction. Addition reactions are different here. Addition reactions. So substitution reactions, this here was with an alkane, right? So this here in red here is alkane, right? This here was alkane, and remember there's still alkenes, alkynes, right? So this here is more so additions are alkenes and alkynes. They undergo a reaction with a molecule, and it's added to the multiple bonds. So what does that mean? So let me do an example in black, and I'll do an example of the simplest double bond we can have. So ethylene, or carbon double bond to carbon, just like this example here, is our simplest double bond. So this here is ethene, or the more common name is ethylene. Don't worry about why it's called ethylene. It's just the common name, because I don't think a lot of people like saying ethene. So it has a, maybe that's why, I'm not really sure, but it's ethylene. It doesn't matter. Both names are fine. IUPAC is ethene, but the common name is ethylene. And what we're doing with addition is we are adding a halogen into this bond, right? So what we're going to do is we're effectively going to break this double bond, and it's going to add some sort of molecule. So usually it's a halogen. Again, it could be Br, Br2, or HBr, or something like that. So let's do the first one here. I'm going to show you what a halogenation is. So halogenation is I'm going to add bromine or chlorine gas. So I'm going to add here, let's add bromine. So this is Br2, and this would be specifically this is a halogenation. It's a subdivision or subcategory of what an addition reaction is. And what a bromine 2 does to this reaction is it's going to add bromine to both sides of this alkene here. So what I'm going to get is I'm going to get something like this. I'm going to get carbon. It's going to break this double bond to carbon. It's going to break. I don't have an alkene anymore. Remember, this here's an alkene. I'm going to actually have a alkane, or a haloalkane to be more specific, or alkyl halide to be more specific. And we'll talk about alkyl halides more probably in the next video. But I'm going to get carbon bond carbon, and then I'm going to get a bromine on one side, or actually a bromine on both carbons here. And this will be just with H's here. So we get something like this. This is a halogenation of ethene, or ethylene in this case. The Br2 adds to both. One bromine adds to the first carbon here, and the other bromine adds to the second carbon here. If I drew a line diagram in this case, I would have this to Br2 would get me something like this. Br and Br, something like this would be my line diagram. I'm drawing the structural diagram, or the condensed, or actually this is just the structural diagram for you in this case, because this might look a little bit more abstract for you viewing this for the first time. So this is an example of a halogenation reaction. And then another one could be a hydrogenation. So what is a hydrogenation reaction? And again, this is still under addition reaction. So a hydrogenation is I'm adding hydrogen to multiple bonds. So let's see here. If I had, I'm going to erase this there. If I had, again, surprise, I'm going to use ethene again. Ethene, or ethylene. And then what if I added hydrogen to it? So this is a hydrogenation reaction. Hydrogenation. If I added a hydrogen to it, what it's going to do, it's going to, again, break this double bond here, and I'm going to saturate, or what it means is I'm going to add hydrogens into my double bond here. So what I get is I'm going to get a single bond, and then the hydrogen is just going to add to both my carbons here. So one hydrogen will add to the first carbon here to make it bonded to 3 carbons, and the other hydrogen is going to bond to this carbon here, and it's going to saturate it to make it 3 carbons as well. So this here is a hydrogenation. In reality, H2 is not enough. We actually need something called a catalyst. And in this case, I don't want to get it wrong, but I think it's a Lindlards catalyst is what we're going to use to hydrogenate an alkene. Or I think this is alkyne actually. I think it's Lindlards catalyst is actually for alkynes. So give me a second. This is actually it works for alkynes. So if I had, for example, a carbon triple bonded carbon, and this is bond H, if I hydrogenate this, hydrogenation, if I wanted to only get an alkene, so if I only want to add hydrogen to one side, I would need something called a Lindlards Lindlards catalyst, or just say Lindlards, and then you'll be fine. And this here, it's just a reagent or a catalyst, and what it does is it helps reduce my my alkynes. So again, this here is an alkyne, and this is also hydrogenation reaction. That's what I'm learning. I'm talking about this. This is alkene. This here is alkyne. So again, the reactions of alkyne as well. And what it does, it reduces, or it hydrogenates this triple bond, and it stops here at the double bond. What I could do is I could actually hydrogenate this even further to get this this thing up here, right? I could do that as well and add a hydrogen again to get this alkane. But what Lindlards catalyst does, what's special about this, is that it only hydrogenates one step. It only goes from triple bond to a double bond, and not double bond to single bond. If I didn't have Lindlards catalyst in this case, I could go from triple bond to double bond, and then it would not stop, and it would go towards the single bond here. So Lindlards catalyst is special, where it only stops at the double bond here. And again, when we start working with catalysts and stuff and reagents, you start to actually see this more and more. So don't worry about the naming for now, but this is just an example of a hydrogenation reactions. It's a hydrogenation of alkene and a hydrogenation of an alkyne. So that's good for the second one here. And let's look at hydrohalogenation. So this is hydrohalogenation, and I'm gonna use the exact same example that they did in the text here. So I have my favorite element compound here. Again, I have ethene, and what I'm gonna do is I'm going to do something called hydrohalogenation. So HBr or HCl works as well. This is a hydrohalogenation. What this does is it adds this Br and adds the H across a double bond or across a triple bond. In this case, it's a double bond. So what it's going to do, it's going to add to this. So one H is going to add here, and one Br is going to add to my second carbon. So I'm breaking my double bond to make a single bond. This H would go to this first one here, and this one would contain my bromine, right? So that's that hydrohalogenation. So that's awesome. So I have three types of reactions here. Let's review. I have hydrogenation. I have halogenation, hydrogenation, and hydrohalogenation. And again, how do we don't memorize this. Br2 is a halogen, we're good. H2 is a hydrogen, so hydrogenation. And hydrohalogenation is just a combination, right? I have H and Br, which means it's a hydro for hydrogen and halogen for Br, so HBr. So now you might ask, Joey, how do you know that the hydrogen goes into the first one and the bromine goes to the second one and not vice versa? Well, in this case, it doesn't really matter, right? Because I can flip this compound in over its head, and I would have the same compound, right? If I flipped this carbon, if I rotated it 180 degrees this way, and I flipped it, it's still the same compound. I still have C double bond C bond H, right? However, in other compounds, and we're going to look at Markovnikovs Rule, which is simply how it states that when does the Br, or when does this molecule, when does this atom bond with which carbon does it bond to? And we're going to learn about that maybe today, actually. Yeah, we'll learn about that actually right after. But let me go over hydration first, which is my last addition reaction before I jump into a specific rule, because Markovnikovs Rule, this rule applies to hydration as well. So let me talk about hydration first before we look at that. So hydration is, again, I'm going to use, guess what? I'm using ethene again. Because again, I only use ethene because it's the simplest double bonded molecule. So it helps you visualize what this is. So what it does is, a hydration would be, I'm adding water to it. The word hydrate, I'm hydrating myself, right? Remember to hydrate yourself. This is a hydration reaction, and it's also addition as well. And what it's going to do is, I'm going to actually redraw water as H bond O bond H, or actually H bond OH. So it helps you visualize this, H bond OH. So what it's going to do, I'm going to highlight this in blue again. This is a hydration reaction. And what it's going to do, it's going to add a hydrogen on one side and then add an OH group or a hydroxyl group. This here is called a hydroxyl group. This OH here is called a hydroxyl group. And then we'll talk about hydroxyl groups later when we talk about alcohols. But what it's going to do is this hydrogen is going to bond to this one, and this OH group is going to bond to the second carbon here. So it's going to give us an alcohol. And we'll talk about alcohols more in the later video. But this is bond H, bond H. This will be bond H, because nothing changes, and this will be bond OH here. So this here will be my alcohol. So it's switches from ethylene, and this is ethanol, but we don't worry about the naming for now. So this is a hydration reaction. So we talked about 4 different addition reactions, and again, these are all addition, right? The first one that was substitution was this. What we talked about, radical halogenation was the first one here, and then this here was halogenation, hydrogenation, hydrohalogenation, and hydration. So again, these 4 reactions are all addition reactions here. So let me talk about Markovnikovs rule very quickly, and then we'll talk about we'll talk about Markovnikovs rule, and then hopefully we can tackle elimination, and then we'll call it a day for reactions of hydrocarbons. And I guess we'll tackle aromatics tomorrow, next session. But let me talk about this idea of Markovnikovs rule, because every time we talk about hydration and hydrohalogenation, we're talking about Markov. We need to know Markovnikovs rule. So what is Markovnikovs rule? So it states that for addition, we're using, when 2 products are possible, we use Markovnikovs rule for addition. So we use Markovnikovs rule. And what it does is it states that when water or a hydrogen halide, which is a hydrohalogen, you can think of it, is added to an alkene or alkyne, the hydrogen atom bonds to the carbon atom that already has the most hydrogen atoms. So I can rewrite this as, if I choose to do a hydration or hydrohalogenation, what it does is the hydrogen will bond to the carbon, the C, with the most hydrogen bonds attached to it. So in other words, we can say that the other thing, that's the halogen or the OH group, the hydroxyl group in this case, and again, the hydroxyl was my OH group, right? The halogen or the hydroxyl group, the OH group, will bond to the carbon that is bonded to the most carbon bonds attached to it. So that's another word of saying another thing of saying Markovnikovs rule, right? So what I like to use is I use a saying called the rich get richer and the poor get poor. That's kind of it's a play on capitalism, unfortunately, but the rich. So let me say the rich gets richer. So rich gets richer. And what does that mean, the rich gets richer? It means that the halogen, the rich stuff, which is the halogen and the hydroxyl group, because they're actually responsible for bonding. So or for property. So we're going to imply that this is the rich stuff. It's going to bond with the carbon that is already bonded to other carbons. The rich get richer. If I have more money, I'm going to obviously make more money because I'm going to invest that money to make more money, right? So the rich get richer. So what does that mean? So let me show you an example. And my example here is I'm going to show you a propene. So this is propene here. So I have a propene. And what I'm going to do is I'm going to do, let me do an example with a halogenation and with a hydrohalogenation or hydration. Sorry, let me do a hydrohalogenation first. So this is HBr, hydrohalogenation. So again, what it states is, again, Markovnikovs rule states that my hydrogen will bond to the carbon with the most hydrogen bonds attached to it. So if I draw my hydrogens, so again, my HBr is going to bond to this double bond, right? It's going to but I'm deciding where does the Br go and where does the H go, right? So let me draw this out. So I'm going to draw out the hydrogens for you. So this one here has one hydrogen, right? This carbon has one hydrogen here. I see two carbon bonds. See two bonds already. So this will have two hydrogens, right? So in this case, my hydrogen is going to bond to the one with the most hydrogen bonds, right? The most hydrogen bonds that are connected is this carbon here. So this carbon is going to get my hydrogen. So I'm going to redraw this, sorry. And again, I'll redraw this and I'm going to write my hydrogen in. And again, it's going to break the double bond, right? So this will now have 3 hydrogens, which means my Br, I'm going to write in red, will bond to this side, right? It's going to go towards this side. So it will have Br will be here. So again, when I say the rich get richer, it means that the halogen that's bonded to the carbon that's bonded to the most carbons, as you can see, this carbon here, carbon 2, is bonded to 1, 2, and 3 carbons, right? It's bonded to 3 other carbons, or there's 3 carbon bonds attached to it, which means the halogen is going to attach to that one. The rich get richer, right? So it's going to attach to this carbon here. And what we can have is, this is the major product, and this is the major product of my Markovnikovs rule. So this is, I'm gonna say this here is the major product. What I could have is, I could have something called anti-Markovnikov. So anti-Markovnikov, as you can see, is the opposite rule. So it's if I have a double bond here and I do HBr again, and halogenation. Or sorry, this is hydrohalogenation. Hydrohalogenation. And if I were to specify that this is anti-Markovnikov, so it doesn't follow the Markovnikov rule, but it's going to follow the opposite. So anti-Markovnikov is going to, then my Br is going to bond to this site instead of the middle site. And then this here is going to get the hydrogen instead. So the Br is going to bond to the one that has the most hydrogen, which is not correct in terms of, it does not obey Markovnikovs rule. And this is a minor product. So what does that mean when I talk about major and minor products? I talk about when I have a major product, when I do this reaction, this hydrogen-halogen reaction, basically 98 to 99% of the time, I'm going to get this product. The 2% of the time is I'm going to get this product here, because hydrogen halogenation is not perfect. Sometimes I do get this, but most of the time I'm going to get the major product here. This exact rule also applies for hydration. So let me do that as well for hydration. So let me highlight this in blue. This is Markovnikov here, and this is anti-Markovnikov, and this is we're still talking about hydrohalogenation, but then this also works with hydration reactions, right? So hydration, if I were to do, this is my water H2O, and I have a hydration reaction. If I were to follow Markovnikovs rule, I'm going to bond to, where is it going to bond? I still have I'm going to have a single bonded single bonded carbon-carbon bond. I still have 3 carbons, but this OH is going to bond to this top one here, right? It's going to bond OH here, and the H is going to bond here, right? Again, the OH is going to bond to the carbon that has the most carbon bonds, right? This carbon here has 1, 2, 3. This here has 1, 2. This one is going to win. So OH is going to bond here. So this is, again, my major product. Major. And then I have anti-Markovnikov of a hydration reaction. So I'm going to have 1, 2, 3 like this. Sorry. And then it's going to go H2O. And then I have, again, this is still a hydration reaction, but it can go anti-Markovnikov. Anti-Markovnikov. And it's going to go 1, 2, 3. And then instead of my OH being at carbon 2, it's going to be at carbon, I guess in this case, it's carbon 1, right? I'm counting from this case. This is OH here, and this here is H here. So this here will be my minor product. minor product. And again, as I said before, 98% of the time, I'm going to get the major. 2% of the time, it's going to be the minor product. And this is what we observe. Chemists observe this ratio as well. So that's Markovnikovs Rule. We have anti-Markovnikov and Markovnikov. And what it is again, when we talk about anti-Markovnikov, I can actually use this reagent, hydrogen peroxide, helps it go anti-Markovnikov. So whenever I need to do an anti-Markovnikov addition, I can use something called hydrogen peroxide to help me do the anti-Markovnikov. Because what if I really wanted this minor product here? What I'm going to do is I'm going to do HBr, and then the reagent here will also be HOOH. So this here is a hydrogen peroxide, and this helps me. This forces it to go minor, so forces it to go anti-Markovnikov. So this is hydrogen peroxide. So like that. So that's just a little note about that as well. So we have all this stuff. We learned about all this stuff today. Someone's, what the F? This is a lot. Again, this is very, very abstract when we talk about Markovnikov and anti-Markovnikov and all these reactions. So let me take the last 4 minutes and summarize what we did, because we did so much today. Look at all this stuff. Sweet. So we did a lot today. So let me review what we did today, so you won't get overwhelmed by what we're doing today. So again, the first thing we did today was we took we reviewed from last week. We took the drawing or the line diagram of our structural diagram, and we named those compounds. So we did that as a review. And then today we did our instead of naming the compounds, we drew the compounds itself. So we drew it like this. So we were given the name pentyne, and we drew out pentyne. So we had 1, 2, 3, 4, 5, and that we knew that the triple bond, the YNE, refers to carbon 1 here. So again, we did that as well. So that here was we drew our chemical compounds based off the chemical names, and we did a bunch of examples with that one. For this one, there was no alkyl group, but this here we had our branched alkyl groups, right? For example, in blue, I did the main chain, right? I did the stuff in the main chain in blue, and in red, I did the side chain stuff, right? So 2, 7, 8, again, at 7 and 8, I had methyl groups, and then the decane refers to the 10 carbon chain single bonded carbons here. So this here was my answer for this one, and we did 2 more questions with with drawing chemical structures. So we did all that stuff. We did one example with the cyclic hydrocarbon, so we drew that as well. And then for the last part of our video, what we did was we did a lot of reactions. We did how many reactions? We did 1, 2, 3, 4, 5. We did 5 reactions, and then we did our rule, right? So let's look at this again. Or actually, we did 6 because we did combustion as well. So let's look at this. So let's review this for the last 2 minutes. Again, the combustion reaction you're familiar with, complete and incomplete combustion. So you learned about in grade 10 and grade 11 chemistry. We're just burning a hydrocarbon and we get water and carbon dioxide, right? This is called complete combustion reaction. We know that. We don't really use that a lot in organic chemistry because we're not making something organic. Or I guess carbon dioxide is organic, but in this case, it's not making something useful that we can make into something else. So that's a combustion reaction. We did our first substitution reaction was we're adding a Cl, or no, we're substituting hydrogen for chlorine, right? We have 4 hydrogens in this case. I'm going to substitute 1 chlorine, and it's going to give me 3 hydrogens and 1 chlorine. And then this reaction, what we can do is we can keep going, right? We can have chloromethane, and then dichloromethane, trichloromethane, and tetrachloroethane, right? I could keep substituting the hydrogens for chlorines till I saturate it, right? Till I can substitute 4 hydrogens for 4 chlorines, right? So this is tetrachloromethane. So I can keep doing this reaction here. This is substitution reaction. And then I looked at all my addition reactions. So I looked at halogenation, where I have Br2 or Cl2. I'm adding to this double bond, right? So this Br2, one bromine is going to attach to the first carbon, the other bromine is going to attach to the second carbon. I make here, this is this is 1,2-dibromo ethene. So don't worry about the naming about this, but we'll name alkyl halides probably next week or something like that. We did a hydrogenation reaction, which was I'm adding H to the 1 hydrogen to this side and 1 to this side. It's going to break this alkene and make this back to an alkane. We did the same thing with an alkyne, for example. An alkyne has a triple bond. We added hydrogen to one side and the other side. I can make it alkene, and then I could actually do another hydrogenation to make it back into an alkane. But then I talked about the Lindlar's catalyst, which stops this hydrogenation at the double bond. So if I only wanted an alkene here, I could use a Lindlar's catalyst and stop it. In terms of it only does one hydrogenation and not two hydrogenations. I did a hydrogen halogenation where I have one hydrogen that goes into the first carbon, and the bromine or the halogen goes into the bonds to the second carbon, right? So I have something like this, and then the same thing, instead of a halogen here, I have a hydroxyl group, which makes it a hydration. I'm adding water or H bond OH to this ethene here. Again, one hydrogen bonds to this first carbon here. The hydroxyl group is going to bond to the second carbon here, and I will make this alcohol. We'll talk about alcohols much later. And there was a rule that we talked about, the rule with hydrohalogenation, the rule with hydration, right? The rich get richer. So that means that the hydrogen will bond to the carbon with the most hydrogen bonds attached to it. So in this case, it would bond to, and I did this case, this H here, this carbon has bonded to two hydrogens, so which means my hydrogen will bond to here to make it 3, and the bromine is going to bond with the carbon that's bonded to the most carbon bonds, which is this carbon here, because it's bonded to 1, 2, and 3 carbons. So my bromine will make it will bond to this the center carbon here. This is Markovnikov, and we talked about anti-Markovnikov, which is the opposite. So we talked about how the bromine could bond to the carbon that's bonded to the most hydrogen atoms if I had in the presence of hydrogen peroxide, right? So this was a reagent that I introduced to you. So this is the major and the minor product. This is the Markovnikov. This is the major, so it follows the rule. Anti-Markovnikov which means we're breaking the rule and we're not using this rule. And this is the minor product as well. This works for hydrohalogenation, and this works for hydration as well. So the exact same rule, but instead of the BR, it was for the OH, right? So instead of the BR here, it was the OH here. So this was a lot. I know a lot of stuff was being covered here. So we're gonna leave off with that. For next week, what we're gonna do, or next session, I'm gonna introduce you to the concept of aromatic hydrocarbons. We'll talk about reactions of aromatic hydrocarbons, and then we'll talk about actually no, we'll do elimination first, because that's a reaction of hydrocarbons that we didn't talk about yet. So we'll talk about this first, and then we'll talk about aromatic compounds. So as always, thank you for watching, and have a great day.